Hi, I'm Thanh, a research engineer from Singapore Management University. Today, I would like to present our work entitled AutoPruner Transformer-based Chronograph Pruning. This is a collaboration work from Singapore Management University, University of Melbourne, and Hanoi University of Science and Technology. For the beginning, let us give a brief introduction of static chronograph. Chronograph is an abstraction of calling relationship between functions in a program, in which nodes are the function and x represent function call between the function. For example, the graph in the slide represents the chronograph of a program with the two objects, person and money. Static chronograph is a chronograph which is statically constructed for representing every possible function call in a program. Static chronograph is a very important data structure, which is seen as the core of many program analysis techniques. Unfortunately, recent work ESEC have reported that static chronograph contain many false positive edges that do not occur at the runtime. For example, Voila, a well-known chronograph generator, had a false positive rate of 76%. Moreover, these false positives also significantly affect the client analysis tool. For example, the experiment of ESEC also shows that 73% of warning produced by client non-pointer analysis is false positive. Meanwhile, the expected from the developers is only 10 to 15%, as reported by Tristan Kiss and Burst in ASE 2016. These results raise an important question. How can we reduce the false positive rate in static chronograph? Particularly, to address this question, ESEC have proposed a new research problem, as they call chronograph pruning. Chronograph pruning problem take input as a chronograph produced by chronograph construction tool such as Voila, and then try to prune the false positive from chronograph to produce a pruned chronograph. Particularly, the solution of chronograph pruning is a chronograph pruner, which works in the workflow in the algorithm 1 in the right side of the slide. Sitting at the core of a chronograph pruner is a classifier C, which is a machine learning model. This classifier is trained in a labeled dataset to predict whether an edge is false positive or not. Then, for each edge in original chronograph, if the edge is false positive, we will automatically remove the edge from the chronograph to produce the pruned chronograph. Particularly, ESEC proposed to use structural characteristics of each edge in a static chronograph to classify whether the edge is false positive or not. Towards this, they first extract 11 types of structural features, as we can see in the slide, then build a decision tree algorithm to classify the edge in chronograph. However, we found that structural features in many cases are failed to distinguish true and false positive edge in chronograph. For example, we can see the function from the accept state in the slide. These functions share the same characteristics that they have a caller, that is the accept state, contain many out edges. This pattern for ESEC is suspicious. As a result, ESEC will automatically remove all function calls from accept state, including the true positive one. Based on the observation, one question comes to our mind. Could we improve the ESEC with additional features to better distinguish between the true and false positive in chronograph? And our solution is based on the principal idea that we can augment the edge features with the so-called of the caller and callee, which is much more informative. However, the challenge is how to extract the so-called features. To address this a challenge. We propose to use deep learning, which has emerges as a powerful feature extractor for text-based documents such as source to automatically extract the source feature. However, deep learning usually requires a lot of training data. Meanwhile, our problem only have a limited data, with the biggest available dataset is 200 programs. So, to address this issue, we propose to use transformer-based model code that is pre-trained on a corpus containing millions of code functions. By this way, the model code can have the basic knowledge about the source code, and then we can easily to transfer the knowledge to solve our problem. Based on the three ideas, we propose AutoPruner, transformer-based code graph pruning. We work in the two main phases, fine-tuning phase and training phase. In the fine-tuning phase, we fine-tune the pre-trained model code to obtain to fine-tune model code, which is adapted version of pre-trained model code to our problem. And then in training phase, we use the model code to extract the semantic features or source features from source code of Conler and Conley of each edge in code graph. Then we leverage the neural classifier which we call feature fusion to combine the structural feature extracted from CD-Pruner and semantic feature extracted fine-tuned model code to obtain the final representation of each edge in code graph. And finally, given the representation, AutoPruner leverages neural classifier to classify whether an edge is false positive. To evaluate the effectiveness of AutoPruner, we answer the question, is AutoPruner effective in pruning false positive from static code graph? To address the question, we use dataset as the same as prior work, NZR datasets, and compare to three baseline: original code graph, CD-Pruner, the state-of-the-art, graph neural network, which is the well-known deep learning model for graph-based problem, which is similar to the code graph pruning. And finally, we evaluate the approach on the evaluation metric recall, precision, and F1, which is standard metric for classification problem. And we can see the result in the slide. And we can see that overall, AutoPruner outperform all baseline and improve the state-of-the-art by up to 13%. The improvement confirm our assumption that so-called feature extracted from transformer-based mode of code can further improve the code graph pruner. Moreover, as our work contains many components and many type features, so we would like to investigate which component of AutoPruner contribute to its overall performance. Particularly, we conduct application study on structural features versus semantic features and Conley feature versus Conley feature. And we can see in the slide is the result, and we can conclude that all features contribute to AutoPruner. And looking into detail, we can see semantic features have a better contribution compared to structural features. Meanwhile, both Conler and Conley function as essential for AutoPruner. And then we also want to further investigate why so-called features and transformer builder code good for this task. Particularly, we use TNSE, a supervised method for visualization, to visualize the semantic feature from the code graph of some simple program. And then in the slide is 3 simple program. And in this figure, the green point is a true positive and red point is a false positive. And you can see that the majority of the green points are clustered and are located relatively close to another one. Furthermore, the cluster of green points are also typically far away from the majority of the red point. And the observation suggests that pre-trained model of code was able to train it to extract semantic features from the Conler and Conley of the function, such that true positive and false positive can be separated from in the vector space. And in the conclusions, in this work, we propose a novel cone graph planner that leverages both structural and semantic features. And we also demonstrate that the usefulness of subcode features extracted from transformer-based model code in cone graph planning problem. And finally, we demonstrate all AutoPruner features positively contribute to overall performance. In the term of future work, we want to investigate three aspects. The first aspect is evaluation. We want to extend our evaluation on other static cone graph analysis and more client analysis. We also want to improve our current model as the design is very simple.